Welcome to the deep dive. We are tackling a topic today that is essentially the next frontier for your personal tech setup. We're talking about building a local AI workstation.
Yeah, which is something a lot of people are, trying to figure out right now.
Exactly. We are pulling directly from a really in-depth document today called the Local AI Hardware Blueprint. And the mission for this deep dive is to basically demystify the exact hardware you actually need to run large language models directly on your own machine in 2026. Because we want to make sure you aren't wasting your budget on the wrong specs or, ending up with a system that just constantly freezes under pressure.
Right, because having local AI running on your own hardware has, well, it's evolved far beyond just being a novelty. When you process your data locally, it guarantees absolute privacy. You are completely disconnected from the cloud.
Which means no API logs.
Zero API logs, no subscription costs, and definitely no tech company using your private documents or code as training data. But that independence is really only valuable if you build the machine strategically. Going in blind usually results in a highly frustrating and honestly a highly expensive mistake.
Which brings us to a massive misconception the blueprint calls the great hardware myth. For the last 2 decades, we've basically been conditioned to believe that if you want a computer to handle incredibly demanding tasks, you just buy a high-end gaming PC.
Right.
You prioritize the fastest processor, the highest clock speed, and just raw compute power. But treating an AI workstation like a gaming PC is completely backward.
Oh, it is the single most common way people waste their budget. Gaming PCs are architected to prioritize raw compute and clock speed to push, high frame rates to a monitor. But applying that exact same architecture to running an LLM locally, it starves the system of what it actually needs.
Because it's a completely different workload.
Exactly. You might buy a top-tier gaming processor, but if the memory architecture is wrong, your AI generation speed will just plummet. You could drop from a really snappy 40 tokens per second down to a painful 2 or 3 tokens per second.
And just to ground those metrics for you, a token is roughly 3/4 of a typical word. So 40 tokens per second is about 30 words a second.
Ugh.
That is faster than you can read. It feels conversational, almost instant.
Yeah, it's a great experience.
But dropping to 2 tokens a second is agonizing. It's like watching someone slowly peck at a keyboard with one finger while you are just sitting there waiting to finish a workflow.
Okay, let's unpack this. If an AI PC shouldn't focus on raw processing speed like a gaming rig, what is the actual priority?
An AI workstation has to prioritize massive short-term memory capacity. Specifically, we're talking about VRAM, or video RAM, which is located on your graphics card. For local AI, your physical graphics memory dictates your total capability. The raw compute speed of the chip is actually secondary.
That's fascinating. It is. The VRAM is what keeps the giant neural network of the AI model readily accessible so the processor can actually execute the logic.
The blueprint uses a kitchen analogy that I think clarifies this perfectly, but we can look at it through a more technical lens.
Yeah.
So in a restaurant kitchen, the chef is your GPU's processing core, the part doing the actual computing.
Right, and the storage room down the hall is your standard system RAM or your hard drive. It holds a lot, but it's slow to access.
And the kitchen counter, the workspace directly in front of the chef, is your VRAM.
Yes, this is the core rule of local AI hardware. A slower GPU with massive VRAM, meaning a slower chef with a massive kitchen counter, will universally outperform a lightning-fast GPU that has inadequate VRAM.
Because if your brilliant chef is working on a counter the size of a postage stamp, they cannot prepare a complex meal.
Exactly. They have to keep walking down the hall to the storage room to swap ingredients in and out. And that constant swapping is exactly what causes that massive drop to 2 tokens a second.
So measuring out how much counter space you need becomes the most critical step. Models are generally categorized by their parameter count. A 7B model has 7 billion parameters, which are essentially the 7 billion variables or instructions the model juggles to generate text. But storing 7 billion parameters takes a massive amount of space. How are we actually fitting these onto consumer graphics cards?
This is where software optimization has radically changed the hardware requirements. We rely heavily on a technique called 4-bit quantization, or 4-bit compression.
How does that work in practice?
Well, in simple terms, quantization reduces the precision of the numbers the AI uses. Imagine taking a highly precise number like pi 3.14159 and just rounding it to 3.14. You save memory space by dropping the extra decimal points, but you still have a highly accurate representation of the concept. By compressing models down to 4-bit integer values, we drastically shrink the memory footprint with near zero noticeable loss in the actual quality of the AI's output.
Even with that compression, the blueprint lays out highly specific VRAM baselines you have to meet. You simply cannot cheat the physics of the memory footprint. If you want to run a 7B model, you need approximately 5 gigabytes of VRAM just to load it. Stepping up to a 14B model requires about 10 gigabytes of VRAM. And if you want to jump to the highly capable 32B parameter models, you need around 20 gigabytes of VRAM.
Keep in mind, those baselines only cover loading the model into memory. That just gets the recipe book open on the kitchen counter.
Here's where it gets really interesting. The blueprint introduces a concept called the threat of context growth, because getting the model running is only step one.
Right. The context window is the technical term for your ongoing conversation history of the AI, the documents you've uploaded, or the code you are actively asking it to review. Under the hood, this is stored in something called the KV cache. Going back to our analogy, if the model is the recipe book on the counter, the KV cache is the actual food you're preparing. As you work, dirty dishes start piling up on the chef's counter.
So if you load a massive PDF for the AI to summarize, those pages are immediately taking up more of your precious VRAM.
Yes, and it aggressively consumes whatever VRAM you have left. Let's say you load a 14B model into a graphics card with 12 gigabytes of VRAM. The model takes up 10 gigabytes, it fits perfectly at launch, and your initial questions are answered at lightning speed. But 20 minutes into a deep workflow, your conversation history grows. The dirty dishes pile up, fill that remaining 2 gigabytes of VRAM, and you hit maximum capacity.
I've actually seen developers experience this firsthand. The mouse starts stuttering, the system fans spin up to maximum, and the whole machine practically locks up.
That is a classic context crash. The system ran out of VRAM and desperately tried to push the overflow data into your slower system RAM or your hard drive. The golden rule here is to always build your machine with surplus VRAM headroom. You aren't just buying enough memory to hold the model. You are buying enough memory to hold the model plus your entire anticipated workflow history.
Knowing that we need all this counter space, how much is this actually going to cost to build? The blueprint outlines specific tiers for 2026, and looking at Tier 1, the entry-level setup is surprisingly accessible. It's targeted between $1,200 and $1,500.
It is a very reasonable entry point for the capability you get, but you have to be incredibly precise with the parts you select.
The blueprint highlights the Nvidia RTX 4060 Ti for this Tier 1 build, emphasizing that it must be the 16 gigabyte version. There is a glaring red letter warning here to avoid the 8 gigabyte variant of that exact same card.
Hardware manufacturers often release multiple versions of the same GPU. The gaming community might opt for the cheaper 8 gigabyte 4060 Ti because it handles standard 1080p gaming perfectly fine. Nvidia built it for gamers. But for AI, that 8 gigabyte card is a complete trap.
Because it cuts your counter space in half.
Exactly. You are immediately having your kitchen counter space. You won't be able to run 14B models, and your context window will fill up almost instantly, even on a 7B model.
Aside from the GPU, the rest of the Tier 1 build acts as a solid support system. You've got a Ryzen 5 CPU, 64 gigabytes of system RAM, and a 2 terabyte solid-state drive. And for your $1,500, this rig comfortably runs 7B to 8B models, which are excellent for localized coding assistance or summarizing text. You can push it to run 14B models, but you have to actively manage that context threat we talked about. Your conversation memory will be much shorter before you hit a wall.
Now, if your workflows demand advanced reasoning, you will want to scale up to the 32B models. The blueprint categorizes this as Tier 2, which covers the power user and pro builds. A 32B reasoning model requires a strategic leap in hardware. 16 gigabytes of VRAM won't cut it anymore. You need a dedicated counter space of 24 gigabytes or more.
The blueprint offers 3 paths to get there. Path 1 is called the smart move, and it's essentially a hardware arbitrage strategy. It involves buying an older, previous generation Nvidia RTX 90 on the used market. But I have to ask, isn't buying a last generation graphics card exactly the opposite of future-proofing your tech?
It seems counterintuitive until you look at the specs. The RTX 3090 may not have the absolute latest architecture or the fastest raw compute speed of the current 40 series cards. However, it possesses 24 gigabytes of VRAM. By buying it used, you acquire that massive memory capacity at a fraction of the cost of a modern flagship GPU.
Which goes back to the core rule.
Exactly. Because adequate VRAM universally trumps raw speed in local AI, the 3090 runs highly complex 32B models remarkably well. It is the most cost-effective way to hit that 24 gigabyte threshold.
Path 2 is the Pro desktop, and this is where budgets start to stretch. We are looking at $5,000 or more. This build utilizes the modern flagship RTX 4090 paired with a high-end Ryzen 9 processor, giving you 24 gigabytes of lightning-fast VRAM and 128 gigabytes of system RAM.
This is tailored for the professional whose time equals money. The 4090 unlocks ultra-fast token generation. But more importantly, the power of this system allows for complex, multi-agent chains. You could have multiple 32B models running simultaneously, verifying each other's work or tackling different parts of a coding project in tandem without hitting memory bottlenecks.
And then we have Path 3, the boss level. This is a $10,000+ investment featuring dual GPU setups, pushing past 64 gigabytes of total VRAM.
We should clarify that this tier is strictly reserved for users actively fine-tuning or training custom models, typically at the 70B parameter scale. If your goal is simply running models for daily automation or analysis, a dual GPU system is severe overkill. The complexity of managing drivers and power draw across two cards isn't worth it unless you specifically need that massive unified memory pool to compute weight updates during model training.
Up to this point, we've entirely focused on traditional PC builds utilizing Nvidia hardware, but the blueprint dedicates a massive section to the Apple Silicon alternative. Mac users have a fundamentally different architectural approach to processing AI.
It is a fascinating divergence in how computers handle memory. The Nvidia PC architecture we've discussed relies on split memory. You have your system RAM on the motherboard for the operating system, and a completely separate pool of VRAM on the graphics card for the AI. Moving data between those two pools creates a bottleneck, but once the data is in the VRAM, the Nvidia architecture prioritizes blistering generation speed. It functions like a sports car, instantly pushing out 30 to 40 tokens per second.
Apple Silicon, however, uses a unified memory pool. The CPU and the GPU share the exact same physical memory space.
This changes the entire dynamic. If you purchase a Mac Studio equipped with 64 gigabytes or 128 gigabytes of unified memory, almost that entire pool can be dynamically allocated as counter space for the AI. You don't have to buy a specialized $2,000 graphics card to get 24 gigabytes of VRAM. The Mac just assigns the memory from its massive central pool.
Wait, the blueprint notes that a Mac outputs a steady 10 to 15 tokens per second. Compared to an Nvidia PC pushing 30 plus, isn't that a massive downgrade? Why would a professional accept that speed trade-off?
You're trading peak speed for massive capacity and power efficiency. An Apple Silicon machine can load a gargantuan 70B model entirely into its unified memory while pulling less than 100 watts of power from your wall. To fit that same model on a PC requires a dual GPU setup putting 600 watts, generating massive heat and noise.
That is a huge difference in power draw.
It really is, and 10 to 15 tokens per second is still perfectly readable in real time. For a lot of users, having the capacity to run a smarter, larger model quietly on a Mac is absolutely worth the slight reduction in text generation speed.
But hardware is just metal and silicon until you install the software. You don't just turn on a custom PC or a Mac Studio and start talking to it. The Blueprint's software optimization matrix dictates exactly how you interact with these machines.
The user experience of local AI has improved drastically over the last few years. You no longer have to write custom Python scripts to load a model. The two dominant engines are Ollama and LM Studio. Ollama is a command line tool. You open your terminal, type a command like Ollama run Llama 3, and it automatically detects your hardware, pulls the model from the internet, and serves it locally. It's lean and heavily favored by developers.
On the other hand, LM Studio provides a full graphical user interface. It looks and feels almost exactly like using a polished web chat application. You have sliders to control how much memory you allocate to the GPU, making the technical backend much more approachable. But the critical software choice actually comes down to the file formats you download.
This is vital. If you attempt to run a poorly optimized format on your hardware, you lose all the benefits of the machine you just built. If you choose the Apple Silicon route, the blueprint dictates that GGUF is your mandatory file format. GGUF was specifically engineered to leverage the CPU and that unified memory architecture on Macs, ensuring maximum compatibility and efficiency.
Conversely, if you built the dedicated Nvidia PC, you want to filter your downloads for the AWQ format.
AWQ is a highly optimized format tailored specifically to exploit the split memory architecture and tensor cores of dedicated Nvidia graphics cards. It maximizes your response time and generation speed. Matching your hardware to its native software format GGUF for Mac, AWQ for PC, is non-negotiable for peak performance.
So what does this all mean? How should you actually apply this blueprint to your daily workflow in 2026? It's tempting to think you should just build a $5,000 PC and run absolutely everything locally. But the blueprint advocates for a much more balanced strategy, the hybrid AI paradigm.
They explain this using a really effective fitness analogy. Your local AI workstation is your home gym. You own it. It securely handles 80% of your daily workflows, summarizing emails, writing boilerplate code, drafting documents. There are no recurring fees, it works without an internet connection, and your privacy is absolute.
Which is incredibly important if you are a lawyer analyzing sensitive case files or a programmer working on proprietary software you can't leak to a cloud server.
Exactly. However, just like a home gym, you likely don't have the space or the budget for the massive, specialized equipment required for every possible exercise. That is where Cloud AI comes in, representing the commercial gym. You reserve Cloud API access for the remaining 20% of your heavy lifting tasks. When you encounter a complex trillion-parameter reasoning problem that your local machine cannot solve, you escalate it to a frontier model like GPT-4 or Claude 3.5. You pay for cloud access only when you truly need overwhelming computational scale.
To make this actionable for you right now, the blueprint concludes with a definitive four-step deployment process. Step 1. Audit hardware first. Don't get distracted by CPU clock speeds. Secure 16 to 24 gigabytes of VRAM on an Nvidia card or a substantial pool of Apple Unified Memory before looking at any other component.
Step 2. Optimize software. Pair the hardware you audited with the correct 4-bit compression formats, GGUF for Mac, AWQ for PC, and manage them through Ollama or LM Studio.
Step 3. Scale responsibly. Don't immediately choke your new system by downloading a massive 32B model. Start with the lightweight 7B or 8B models. Push them hard to see how your specific system handles the context growth and the KV cache before you attempt those longer reasoning chains.
And finally, step 4, deploy the hybrid workflow. Route your private, sensitive data locally to your home gym and deliberately escalate only the most complex reasoning problems to the commercial gym of cloud APIs.
It's a remarkably practical approach.
If we connect this to the bigger picture, mastering this blueprint is ultimately about taking ownership of your digital tools. By understanding the physical limitations of VRAM and mechanics of local memory, you free yourself from blindly relying on endless cloud subscriptions. You bypass the marketing traps of gaming hardware, and you build a machine optimized exactly for your cognitive workflows.
It changes your relationship with the technology from being a renter to being an owner. Which leaves me with a final, provocative thought for you to ponder. As local quantization techniques inevitably improve, and our home gym hardware becomes capable of handling 90 or even 95% of our daily tasks without breaking a sweat, what happens to the massive multi-billion-dollar cloud models? Will the fundamental desire for absolute data privacy and zero recurring costs ultimately outcompete the sheer computational scale of big tech? It is something to think about as you evaluate your own setup. Thank you for joining us on this deep dive. Before your next big workflow, take a second to check your own PC's counter space. We will catch you next time.